Good morning, or good afternoon, good evening, good night, wherever you are. This is a new YouTube video in a series. It's sort of an update of my latest research. I've been exploring really the what might be going on inside the nucleus of an atom. So is there a nuclear force? Is there no nuclear force? It's kind of a fairly hot topic because recently there's been a resurgence of interest in sort of electromagnetic models of nuclei. So the argument there is that what happens inside of a nucleus might also be explained by the electromagnetic force, and that makes it possible to then have what they call low energy nuclear reactions. You might sort of get mutations inside of a nucleus, transmutations by using laser or other electromagnetic radiation. So I think the numbers don't work out. The distances, the scales that are involved suggest a much larger force. So that's what we refer to as the nuclear force. I've done some calculations. They should not be so difficult. It's more sort of to give you an intuitive feel of how one might approach these things without sort of resorting to quarks and other sort of highly advanced mathematical techniques. On this first slide here, I present forces. They act on charges. If we have, the electromagnetic force for sure acts on electric charges. If they're the same charges, both positive or both negative, they will repel each other. If they're opposite, they will attract each other. We have a formula there, a proportionality constant, sort of defines the nature of the force. And we know the electromagnetic force is a conservative force, conserves energy in the field. And so it sort of dies down within R square, with R square. So we have an inverse square law, and that makes it all nicely symmetric and makes it also nice, very easy to, model it relativistically. The magnetic force might be a relativistic effect of the electric force, and so on and so on. So we're going to examine if there's a nuclear force, what charge does it act on inside the nucleus? Does it act on electric charge, or should we invent some kind of nuclear charge? And so we're going to have a look at that. The key is a bit analyzing what goes on inside the deuteron. That's the nucleus of deuterium, the heavier water. On the top right hand side there, I put what's sort of commonly referred to as the Zitterbewegung model. It's sort of a mass without mass model to explain mass energies of elementary particles. The illustration comes from the research group of Celani, who's done a lot of research on that, who's also heavily engaged in that, what I mentioned, low energy nuclear reactions, anomalous heat reactions, and these kind of things. So I will not acknowledge everywhere sort of where I get the figures from. Most come from Wikipedia, or from Celani, or from other sources you can find. So apart from examining deuteron, the nucleus of the heavy water atom, which we should explain first, I think, before you get into more complicated nuclei. There's also this hypothesis that the neutron might be some combination of a proton, basically a positive charge, and an electron. Both would have different form factors, which explains why they don't annihilate, because matter antimatter, they annihilate. The charges are opposite, but they also need to sort of be exactly the same size, same form factor, just opposite spin. So I mentioned at the bottom there my list of publications on ResearchGate, and what I'm going to explain is basically sort of a summary of my last paper. All right, I will move to the next slide. So my slides are heavily stuffed. Sorry for that. So the hypothesis there really is neutron is a proton plus what we call a Zitterbewegung electron, a negative charge tittering around, moving around. That's reflected there on the right hand side, the structure of the neutron. That's basically an illustration from Hofstadter and Mössebauer, who got a Nobel Prize for their electron scattering, the measurement of sizes of radii of nuclei and nucleons by shining, beaming electrons at them. The hypothesis there really is indeed sort of that a neutron would be, would have a core positive charge, a proton, and then what is mentioned there is sort of like, a negative meson cloud. I find the word not really appropriate as a meson. I'll explain that when I discuss the energies that we need to look at. But yeah, on the right hand side, they really have these form factors that I mentioned. Right? So the charge radius of a neutron is 0. It's a neutral particle, but it has a magnetic moment. So yes, it does scatter electrons. I think by some kind of by magnetic moment of the electron, magnetic moment of the neutron, and so there's a deflection there, and we have a sort of an effective interaction radius, as I call it. Let's look at the numbers, the measurements. We know that a neutron decays into a proton, and a muon electron. It decays in two stable products, basically a proton and an electron in the end, by emitting neutrinos, occasionally in horizontal reactions, but basically neutrinos, and that sort of also indicates that we might have something else there, another force, because photons they carry the electromagnetic force. They're point-like particles, light particles. Carrying the electromagnetic force, but neutrinos we don't quite know what they are, and thinking of a nuclear charge inside of the nucleus would also helps to explain why we have neutrinos in those reactions. But it's not stable. The energy difference is about 1.3 mega electron volt. That's about 2.5 times the energy of a free electron, about 511,000 electron volt. But it's only a fraction of what is commonly referred to as p mesons, plus or minus, which is about 148 mega electron volt. And it's also a tiny fraction, really, of a muon electron. So I don't think the term meson cloud or meson is really appropriate. You're really thinking of some kind of electron, basically. But with about 2.5 times the energy of a free electron. So what's the extra energy? It must be binding energy, and that gets released indeed when a neutron decays. We also have, as said, the deuteron. When you look at that, there we have a stable configuration, because the energy difference between the two constituents of a deuteron, neutron, and a proton, and the deuterium nucleus itself is negative. So we have the energy of the whole is lower than its constituency. So that explains why we have a stable nucleus. I think these are basic values, so we need to explain those energies in terms of orbitals. I'll talk about that. Orbital energies. When we think all of the energy is in the oscillation of a charge, then we need to explain, what kind of orbitals are there, what kind of forces are there, and how can we approach that? The puzzling thing in the whole thing is, of course, an electron is rather large. Free electron, we think of it as tittering around in a fairly large orbit, about 386 femtometer, the picometer scale, pretty large. Even if we think of sort of hard Compton scattering, the hardcore charge inside, it's much larger than the radius of a proton or a neutron, 2.82 femtometer. The radius of free electron and the classical electron, the charge itself is explained by alpha, the fine structure constant. That also explains, according to me, the anomaly and the magnetic moment and all these kind of things, but I'll refer you to my papers for that. But it's kind of puzzling. We have something that is light and fairly large inside something that is rather small. So people try to model that. They did assume, you know, different potentials, different forces, and one of them is Yukawa's nuclear potential function, which I will talk. We've analyzed it. My view was always that a bit, you know, if you assume a different potential, different force, then you need to sort of assume a different charge. At the same time, if you want to be adding forces and potentials, then you actually need to assume that they act on the same charge. So that would be the electric charge then. So how do you go about that then, and how do you model that? You want to stay away. I mean, I want to stay away from, like, you know, assuming superluminal speeds of orbit, superluminal tangential speeds. I also sort of want to stay away from assuming that, you know, there might be like a nuclear equivalent of Planck's quantum of action. So I want to do sort of more of a classical analysis. But the fact of the matter is, when you do such you know, mass without mass models, and you calculate distances, and then you arrive at different scales. The radius you get out of your Zitterbewegung model for a proton or for a neutron is sort of, you know, very, very small. But when we're talking about these energies here, you know, the mass about 2.2 mega electron volt for the difference between you know, the energy of the deuterium nucleus and its constituencies, then, you know, you get oscillations. If they would have to sort of pack that energy, you know, these orbits would be pretty large. So 88.70 femtometer for neutron proton dance inside of a nucleus. And if we think of a neutron as a proton and a Zitterbewegung electron, because its mass, its energy is lower, you get an even larger radius. That's something fascinating about that quantum radius that we calculate for elementary particles, is that, you know, larger the mass, larger the energy, the smaller stuff gets. So okay, so try to keep these numbers in mind, and sort of vaguely try to understand that we you know, we get indeed sort of scales then and distances, and that don't make sense in terms of you know, explaining those rather large energy values. They're not huge, huh? 2.5 times the energy of a free electron is not huge, but we need something that is more consistent. This is a lot of complicated formulas, but they're not so complicated actually. On the right hand side, on the top there, we have Kepler's laws that you know, calculate the period of an orbital, whether it be, you know, two planets circling around each other, or you know, an electron and a proton that are holding each other together by an electromagnetic force, or what we probably assume is a nuclear force holding stuff together, or at least, you know, an interaction between the nuclear and electromagnetic force, creating some kind of potential well in which you know, the two are bound and can lower their energy together by moving around each other. So it quickly gets very complicated. We'll assume zero spin particles, so they don't have any spin on their own. There's only angular momentum, sort of on the bottom right corner there. But you can see, you know, if you would have spin, you would have precession and other things, and magnetic moments coupling and all these kind of things. We'll steer clear of that. The central figure there is sort of a polar rose, just to illustrate that, you know, you can have very different orbitals. I think the main difference between the Bohr-Rutherford model of a hydrogen atom and Schrödinger's equation is that Schrödinger's equation basically models, you know, non-circular orbitals, elliptical, or, you know, other stuff that has you know, different eccentricities and different accelerations. We'll talk about that. Well, we'll talk about straight away. You know, what is a force? It's the time rate of change of the momentum. So the derivative of p, the momentum, with regard to time, and then You can work that all out. We know we need to be relativistically correct, so we'll use the relativistic mass. So that's gamma, the Lorentz factor, times the rest mass, the zero rest mass. When we're talking, a mass without mass model. Now we can expand that and use the chain rule, etc., etc., and you'll arrive at sort of that the force should be equal to gamma squared times the relativistic mass. Mass increases with velocity times the acceleration. And for complicated orbitals, we can have the acceleration of the acceleration, and then second, third, fourth order derivatives. I'll go down now. The Kepler's law for orbital energy. You may not have seen that, but it sort of sums up all of his stuff. The equations on the top there give you an angular momentum formula. You also have that standard parameter for gravitation, or the electromagnetic force. We'll have something like that from the period, from the formula for the period. And the frequency, you can see that's going to always be equal to the angular frequency squared times the radius. The A is there, the radius of the orbit cubed on the cube to the power 3. The interesting thing about law for orbital energy is that we're gonna look at it. The energy, we're gonna divide it by its mass, by its relativistic mass, and we know there is an equivalence there. It's equal to c squared, and the energy of an orbital. That's what Kepler saw, is that you can analyze that in terms of the sum of two energies, the kinetic energy, which depends on the velocity, which is on average that's about half. We have an oscillation, so in an oscillation about half of the energy on average over a whole cycle, a whole orbital cycle, that will be half the energy will be kinetic and half the energy will be potential. So the potential is because of the attractive force, we have a negative potential. So we have that mu there, the standard parameter. Said we'll have one for gravitation, for the electromagnetic force, and we'll also calculate one. I will give you a formula at least for nuclear force, and we divide that by the radius. So potential energy depends on the position, on the distance to the center of the orbital, or the focal point if it's an elliptical orbital. And underneath, I just give you a dimensional analysis of the same formula, just to make sure that we're indeed right in these formulas. So basically, v squared divided by 2 minus the gravitational constant times the mass of the mass at the center, and the mass of the planet that's orbiting around it, divided by an extra mass factor there. I'll explain that later. But in case it works out, you sort of look at these dimensions, kg for mass. It's mass comes in one color only. That's what made Einstein doubt a bit, that there is such thing as mass. Really, maybe everything is energy. The electric charge comes in two colors, plus and minus. But in case for all these equations, it works out. So we get m squared meter squared divided by second squared. And so that's fine. So the on the left-hand side, on these formulas are basically an expansion of the energy. So the ratio of between energy and mass is always equal to c squared. So if we take mc squared relativistic mass times c squared, we can expand that using the formula for relativistic mass, which is on top of our polar rows. We have a formula there for the radius as a function of the phase of the oscillation, but you can look that up in the paper. That's all very consistent. But that formula is indeed the mass is the rest mass divided by the Lorentz factor, and then we can expand that using the binomial formula. So then we can put it all back in there, and that's what we get on the left-hand side. Power series with the beta is there, the v divided by c, so it's velocity measured as a number between 0 and 1. So if we then move to, and that's going to be the trick of the game actually, is to move from mass to charges. So the potential energy formula then is written as the charge squared. It's just like multiplying two masses. Of course, we have our proportionality factor with the electric constant there. 1 divided by 4p epsilon 0 times 1 over r, right? There's often confusion in these formulas when you start calculating what's the difference between energy. Well, the energy is, when you put a charge inside of the field, right? So you'll have an extra q, the charge you bring inside of the potential field. And so the potential itself, we have to divide by that charge again, the electric charge. So then you get a formula which only has q, not a q squared in the formula. So kinetic energy basically relativistically is defined as the difference between the total energy, which is always mc squared, minus the potential energy. So you can work that all out. We use the mc squared formula that we have on the top left-hand corner there, and then we take that Coulomb potential, and we subtract that from the total energy, and then we get another power expansion, almost the same formula but without factor 1. And yeah, you have b squared, b to the power 4, etc. Basically, we're gonna interpret these as different, second, fourth, etc. orders of the position vector. So you have acceleration, and then acceleration itself might have a non-zero derivative in a more complicated orbital. That's all I'm gonna say about these formulas for the moment. As you can see, it's not really rocket science. There's a bit of vector algebra there, well, not very much, just a vector cross product. Angular momentum is interesting, the L there. So I equate it always to that's the Planck-Einstein law that gets incorporated there. It must be a multiple of Planck's quantum of action, the reduced quantum of action, because we're talking angular momentum. And yes, from Planck-Einstein relation, we know that the energy is h times the frequency. So Planck's quantum of action must be the energy divided by the frequency. So for the rest, I'm doing nothing special there. I also do a dimensional analysis for the period t to show that it works out nicely, and now we get something in seconds. The other formula there, R, is a combination of things. With E is not Euler's number, but is the eccentricity of the orbital. The delta is the phase again, mu the standard parameter. Yeah, that's about it. All very basic equations. So here we get to the meat of the matter, I would say. So the graph is there is very central. So that graph basically gives you the potential functions. And the red one is the Coulomb potential, which I denote as the force that is based on the potential. If we integrate, then we get the Coulomb force. Sorry, if we take a derivative, the Coulomb force. And then we assume there is some kind of a nuclear force, and that's where I differ with Yukawa's thing. These two potential lines, the forces, the magnitude of the forces, they must cross. At some point, if you get close enough, you must get a potential well. So these potential functions, the force functions, must cross each other. And to do that, actually, you cannot assume a 1 over r law for the potential, or a 1 over r squared, an inverse cube law, an inverse square law for the nuclear force, because otherwise you never get that crossing. The Kepler's laws there again, the energy that is in an orbital are given there. First, the black one, formula in black, E divided by mc squared, and then again, the product of the masses, the 1 over r factor. We know that one, and so basically we're going to move from masses to charges. So instead of a gravitational constant, we have the electric constant, but we basically have the same formula, and that's where these formulas don't work out if you don't talk about energy divided by the mass factor. And so that's where we use Einstein's energy mass equivalent. and where we sort of, the crux of the matter of this whole thing is moving from, mass and thinking in terms of equivalent energy, the energy that is in the field. So that's where we get the red formula and the red curve in the illustration at the center in the graph, which I made with Desmus. I think is the only original illustration in this presentation. So then you have a bit of a monster underneath there, which tries to do the same for a nuclear potential. So basically what we do there is again think in terms of some kind of nuclear field, and so we have, well, what I assume there is some kind of nuclear charge, but it must be acting on the same electric charge, so that Gn there, the nuclear charge, it must be the electric charge. That has implications, of course, for our nuclear constant. Now we have an electric constant, we have a gravitational constant, so I put there a Kn nuclear constant, from which we can, then we can think of it in terms of some kind of nuclear permittivity of space-time, maybe. But it's actually going to differ only from the electric constant by that range parameter. I said from some kind of distance a, we must find that nuclear charge, again acting on electric charges and sort of it must work the other way around in terms of the nuclear charge is going to attract two opposite electric charges, but it's going to keep two opposite electric charges together. So you've got a bit of a game there with the signs, and you need to sort of keep track of the sign conventions, but it works around. And you can think of sort of distance functions, 1 over r, 1 over r squared, 1 over r3, 1 over r4, but it doesn't really matter because in the end it falls away. You take higher order powers of a of the distance, and you need to take higher order powers of higher order powers of the scaling parameter a. You need to take higher order powers of r also. So in the end, you're going to have, the assumption is going to be that our nuclear potential is a, that scaling parameter, divided by r squared, and so its physical dimension works out because a is measured in meters, distance units. R squared is mentioned in meters squared. So the dimensions work out again. So I put that there all at the bottom in small letters there. Again, a dimensional analysis, half of physics, or thinking about formulas is dimensional analysis. So if I've done that consistently, I hope. So that's what we get there, really. You see on that figure, indeed the potentials cross when the forces are equal and opposite, the nuclear force and the Coulomb force. So that means that the distance to the center r must be equal to that scaling parameter. R is equal to a. You can see that. I put a at the point about 0.3 on this function without the nuclear parameter or proportionality factor, and then the electric proportionality factor. So yeah, it's about 0.3. You can play with it, but it's always going to be the same thing. The two forces are going to be equal and opposite if your distance from the center is equal to your scaling parameter a. The nice thing about the two functions is that, as you would expect, is that the nuclear force sort of is very strong at close distance, but goes to 0 when you move away, and that sort of gives the result you want, is that the difference between the two potentials goes to 0 actually. So basically we get a 1 over r potential, combined potential for large distance. The large distances are values of r that are much larger than that scaling parameter a. The tricky thing is indeed with the nuclear force is that that has severe implications. Is it falls away not with an inverse square law, but with an inverse cube law, and we know energy conservation. Energy must be conserved in the field, so you'll have an asymmetric nuclear field there, and that's something I haven't worked on. But that must be the case. We have a potential there that is non-symmetric, non-radial. So we won't have sort of a spherical equipotential lines. So that gives rise then to sort of disk-like structures and all these kind of things, which is okay in the end because orbitals and oscillations are in 2 dimensions, right? So okay. So that's basically the model. So we've come to the conclusion that a nuclear force must exist, because yeah, we need to explain why 2 protons, like charges, if there's a proton inside of a neutron and in a deuteron nucleus, that neutron and the proton stays together. Then the sort of the electron must act as some kind of glue there. Between the 2 protons and all that kind of stuff. So it is a logical model. The next steps we need to take there is we need to analyze this further. We need to sort of think about the nature of the force, its structure. So that's probably where if you think about those ratios between the charge that gives rise to the force, I said the electric charge and nuclear charge. But they differ only because of that scaling parameter we said. Their equivalent energy is there's a mass equivalent of that energy in the force field. So what do these ratios mean, and what does it imply for the structure? We should also do some thinking about these potentials. They go to infinity at the center. At the distance r is 0. But you can see that the infinity for the 1 over r function and the a over r square function is kind of different. We have different infinities. It goes back to an idea of Leibniz, who invented differential calculus and the instrument of integrals, infinite sums, is that you can have different infinities. The limit will give you infinity, but when you start taking ratios of these things, then you get non-infinite ratios. So yeah, think about the natures of the singularities. At the center, it's kind of probably here you might invoke black holes. Black holes have also a radius. So the r is 0 distance doesn't really exist, maybe, and all these kind of things. So that's sort of further work to be done, kind of philosophical work. There's actually a lot of publications on that which are interesting. So you can Google these. I give some references in my paper as well. The interesting thing is sort of we've got a static model here. Our charges don't move, so to speak. Well, they actually do, but they're sort of in a cycle, and so we look at that cycle. We don't have a time-dependent potential. We have a charge at the center, which creates a potential field, and so it's a scalar potential. And so now you might want to think about giving that potential, a time-variant bit. And as we know in electromagnetic theory, we'll use the Lorentz gauge. Basically, you can see that we'll have a vector potential, moles the magnetic force, from which we can derive the magnetic force. The magnetic force is there because there's motion, charges in motion. And for the electromagnetic field, we'll use the Lorentz gauge. The question is, as I said, because we have a different beast here, it sort of acts on the electric charge, but the force is opposite. Can we use that Lorentz gauge? Probably not. That might have implications for the Schrödinger equation. Also, I think that once you've got the structure of the force right, by finding the gauge for that nuclear force, for the time variant bit at least, then you'll probably can use sort of the general Schrödinger equation for a nuclear oscillation. So I put it there. It's basically I substitute in Schrödinger's equation for the model of hydrogen atom. I just substitute the potential for the nuclear potential. The wave function can always be written as a sum. There's the superposition rule. So basically we write it in terms of complex numbers. We'll have and r, the radius of that oscillation, which will vary in time. So yeah, then you have symmetric orbitals and non-symmetric orbitals, etc. But you can substitute all that, and basically then you have, Schrödinger's equation in terms of simple coordinates. Usually spherical coordinates. R will be x, y, z. We can write them in terms of polar or spherical coordinates or Cartesian coordinates, but spherical coordinates make the calculations easier. So that should sort of be then an equation for a nuclear oscillation for our neutron model, I guess, the proton and the electron orbiting around each other, the proton being the very massive charge at the center, and the electron sort of the lightweight negative charge going around it. So I haven't started to sort of think about solutions because even Schrödinger's equation for the hydrogen atom is very, very complicated to solve. But that's it basically. I would just want to end with a few critical remarks on what I started with, is sort of the hype or all the research that's going on low energy nuclear reactions. If there's really a nuclear force, and we've got neutrinos, then you need to sort of bring neutrinos in, or other, you need to assume there's a strong force, and then there will be strong oscillations, and it remains to be seen how you can have transmutations or nuclear reactions with with photons, with laser stuff, and probably there is an element of creating transients inside that can break the nuclear bond, or break a potential wall. Potential walls are dynamic. There will be temporarily a hole in a wall. A wall goes up and goes down. It's like firing bullets at a very fast rotating propeller of an airplane. The bullets will get through or they won't get through depending on the speed of the bullet. But yeah, if you have low energy bullets, low frequencies, how are they going to get through the potential wall? So that's the critical note, and that's sort of where I want to further analyze a bit the literature. And but I'm going to call it a day here. I'm going to call the presentation. It's almost 40 minutes. I hope you enjoyed it. I'm going to upload this now. I may redo it, might not redo it. If you like it, let me know. If you think there's sort of errors in the logic, let me know too. My email address is somewhere, or you can message via ResearchGate or wherever. Okay, thank you for listening. If you made it till here, then that's hat off. Congratulations. Thank you.